Good afternoon and welcome to my poster. And I'm Chenqi, and today I will be talking about EEG and body posture-based multimodal emotion recognition. So as some of you might be familiar, EEG is a common method to monitor electrical activity in the brain. As you can see here, I'm holding a 5-channel EEG device from Emotive that we're currently using. And with the device, we can visualize the data with the input data as shown here. And by body posture, we're referring to the computer vision technique to segment body parts in order to determine one's posture, which you can get a better idea by looking at figure 2 on the right. So now you're wondering, why do we need emotion recognition? Well, understanding the message that is being communicated is equally important as the context. So just like natural language processing, emotion recognition will be a critical step towards more natural human-computer interaction. However, it is not an easy task. Current state-of-the-art EEG-based unimodal accuracies range from 60% to mid-80% for two-class classification. And even though multimodal approaches can achieve higher accuracies, but they involve invasive physiological sensors or facial data, which are not easily accessible while wearing face masks. So with the problem in mind, we're proposing an EEG and body posture-based approach, which is expected to improve unimodal accuracies. As research has shown that human posture is a major nonverbal communication of emotion. This approach is also adaptable to social distancing as it involves minimal physical contact with sensors. A potential drawback of the system is that it is not fully contactless. Another problem is the need for a large data set to fully capture the relationship between posture and emotion. This is because we have a variety of different reactions corresponding to different emotions, and they can even evolve in the long term. So now you have in front of you the experiment workflows through which we follow. The first step is somehow to elicit a certain type of emotion within our participants, and this was done so with the help from the OASIS dataset. Here are 2 example images, and we chose OASIS because it is a modern free-to-public dataset of images that is designed to elicit a variety of emotions. As the images were shown to the participants, EEG signals are recorded with the Emotive Inside headset, and upper body movements are collected with a simple webcam. Here is an example of the data collected, and on the left you can see raw EEG signals from the 5 channels, and on the right is the head orientation data in the form of quaternion, magnetometer, and acceleration. In step 3, the EEG data are then pre-processed with independent component analysis and filtering. The video segments are also labeled according to Ekman's 6 basic emotions with a crowdsourcing approach, taking the majority as the label. And since we have subjective interpretation of other people's emotion, we ask the participant to rate their own emotion as well. At the same time, the video is analyzed with a mobile net-based architecture to estimate their posture. Finally, the last step that we are yet to reach is training and testing of classifiers with the collected data. We're still collecting and pre-processing more data, but some of the approaches that we have considered include a comparison between traditional machine learning approaches like SVM and deep learning approaches like recurrent neural networks. So following the procedure, we have so far collected data on 3 participants, making up a total of 60 minutes of recording, composed of approximately 360 10-second labeled segments of pre-processed EEG and body posture extraction from the videos. The figure on the left is an example of the pre-processed data, and the figure on the right is a power spectral density diagram of the pre-processed data. You can see a spike at 10 Hz, which does not exist before pre-processing, and this is an indicator of good pre-processing, as this is the alpha frequency related to participants' state of cognitive stress. So in conclusion, the significance of our new multimodal dataset is a novel approach to emotion recognition, such that it requires minimal physical contact with participants and adaptable to social distancing. A significant next milestone would be to verify whether the new dataset can help to create a model that achieves or even improve on the state-of-the-art classification accuracies. To do so, it will involve more data collection as the next step. Placing our work in a broader context, it has the potential to help study the very nature of human emotion from a behavioral science perspective. This dataset could perhaps be useful for developing models that pick up minute gestures that are good signs of emotions. A more ambitious next step is to explore a fully contactless system, which would involve a remote EEG sensors. So thank you so much for listening, and please let me know if you have any questions, and I hope you enjoy the rest of the conference.
Thank you, Chenqi, for your presentation. So now I would like to address the judges and ask if you have any questions. Could you please unmute and ask them now?
I can start things off just by asking a question. So you're considering, I suppose, a broad range of emotions, but maybe is there any specific emotion that you're going to plan on targeting first to maybe focus in on?
Yeah, so we have a data set we're planning to label based on the 6 different emotions of Paul Ekman, which are fear, anger, sadness, disgust, and surprise. So, and we're hoping maybe we can also look at the valence and arousal model, but that would be a continuous data.
So I'm not very familiar with this. So how does the EEG work?
Basically, this is like a device with multiple electrodes, and there's a reference node, as you can see here, and the different electrodes will be measured against the reference node on your skull to see the electrical activity of your brain.
And so then how does how is emotion related to the electrical activity?
It's not very clear, but looking at the signal, that's where we're planning to apply machine learning models to pick up features from the different